All right, hey, this is Dr. Butler, and we are going to do a demonstration of the conservation of momentum and the conservation of energy using collisions. What I have set up here is I have an air track. If I turn on the air, you can barely hear me. As I push one cart, which is going to be this one, which is almost nearly frictionless, it's going to go through one photogate timer, which is going to measure the time it takes to pass from one edge to the other edge of this block, because it's going to pass through this infrared light and block that light, and the timer will know how long that's blocked for. On the Logger Pro, which is down here, we have set up photogate timer distance is that distance is 0.04 meters, and it automatically tells you the velocity. This was an experiment I did where all I did was push one cart without collision through the timers. Went through timer 1 and went through timer 2. Both ended up being 0.259 meters per second, if you can see that right there. So what we're going to do is I'm going to push a cart that has the same mass. It's going to collide into a second cart. They both have Velcro on them. And so when they collide, they will stick together and they will continue moving through there. We will be able to find out what the speed is of the first cart before through timer 1. We will be able to figure out the speed of both carts combined as they go through timer 2. And then by using those speeds, we should be able to get what is the momentum of these things. So first of all, I am going to measure the mass of each cart, so we can see where we are. Cart 1 has a mass of 239 grams, or 0.239 kilograms. Cart 2 has a mass of 222 grams, or 0.222 kilograms. They are nearly the same. There is a slight difference because of the difference in manufacturing, and that one cart has timer control on top of it and the other cart doesn't. So as a nearly the same mass cart hits a second cart of almost the same mass, what is going to be the speed going out? Using conservation of momentum, we should be able to get this. The total momentum of the system before is all in cart 1. The total momentum in after is going to be the total momentum in both carts combined, because both will be moving. All right, so I will show you the demo. We'll look at the numbers and see if indeed they come out to be about the same. So I'm going to turn on the air right here. I'm going to push play, and then I'm going to release the cart. And stop. So we see that the velocity, I actually have these two timers are mixed up. They're in reverse order. The photogate, the velocity 2 refers to the cart 1, and the velocity 1 refers to cart 2. I should have those switched. In the next demo, maybe I can do that. So 0.539 meters per second is the velocity for the cart by itself. 0.240 meters per second is the velocity for the cart system after. All right, so let's do some calculations with this. If you can see, I have the mass of 1 and the mass of 2 right here. Before the collision, we had only mass 1 of the cart, and we had the velocity of the cart, which is going to equal the momentum of the cart before. And if I calculate that, our velocity 1 was 0.539 meters per second, and the mass was 0.239 kilograms. So if we calculate that, total momentum is 0.129 kilograms meters per second. That is the mass before. After, our mass is both m1 and m2, and we're going to multiply that by the velocity after, and we're going to see what that total, that is our momentum after. So if we calculate that, the combined masses is 0.239 plus 0.222 is 0.461 times the velocity, which was 0.240, and the momentum afterwards is is 0.111 kilograms meters per second. So conservation of momentum would say that the momentum before and the momentum after should equal. You realize that they don't equal. Well, that could be due to many things. Most likely in a situation like this, the collision causes some friction with the outside, and as a result you lose some momentum because of that. And if your after momentum is less than your before momentum, it makes sense because there might be some transfer of momentum to the outside. If your after momentum is higher than your before momentum, then that's not going to make much sense. So there you go. Demo 1. All right, now we are going to do this experiment again. But this time I added some extra weights onto mass 1. So let's remass the first one. And instead of what we had before, now we have 0.440 grams, which is 0.440 kilograms. And our mass 2 is still 0.222 kilograms. So mass 1 is now nearly double mass 2. So what we're going to do is we're going to collide these into each other. So mass 1 is going to come, which is double the mass, and it's going to hit mass 2, and then mass 1 and mass 2 together are going to travel. What I would like you to do right now is pause the video and see if you can predict what you think the velocity should be, and then we'll measure and see if it indeed is that. All right, so I am going to actually work this out for you right now. The momentum before should be m1 times v1, and we have to figure out what that velocity is going to be before, and I will do that experiment. All right, and without you looking at the screen, our velocity, oh, I forgot to push play. We have the same velocities as we had before. I forgot to push the play button, and we'll do this one more time. All right, without looking at the velocities in particular, we notice that velocity 1 is 0.417 meters per second. Now would be a good time to pause and see what the velocity 2 should be. And I'm going to calculate that. So mass 1 times velocity 1 should be 183 kilograms meters per second, keeping the 3 significant figures. Momentum after, according to conservation of momentum, should be the same. which is 1.83 kilograms meters per second. But that is the combined mass of 1 and 2 times the velocity of 2. And we want to know, what is our prediction for velocity 2? So we take this and we use our masses and we combine them, which is going to be 0.662 kilograms times velocity 2, and solve for velocity 2, which is 0.662 divided by 0.183, gives us 3. Sorry, I did that math wrong. 0.183 divided by 0.662 gives us 0.276 meters per second. And we look at our velocity 2 on here, and it says 0.271 meters per second. Within one significant digit, we had the right answer. And that shows conservation of momentum. I leave it to you to think of this. What would happen? Well, I will do it. What happens if we reverse the weight on this? And so I'm going to take the extra weight and put it on the second one instead of the first one, so that the second one is double the mass. What do you predict? What's going to happen to the velocity? Is the velocity going to go up? Is it going to go down? Or what will happen to the velocity? Without doing the calculations, I will set this up and time it. So we'll give it some speed, it will hit the second, and they will both collide together. So here, our first velocity was 0.427, which isn't too far away from what we have, but our velocity went all the way down to 0.122, which is a fraction of 0.122 divided by 0.427, which is about 1/4 or 1/3 of the velocity of the of it in the beginning. Because you had more mass in the end, the momentum is still the same at the end than it is in the beginning, but you have those things. There you go. That is your demonstration on conservation of momentum. We could also do this where the carts bounce from each other and you measure the kinetic energy as well. We are not going to do that because that's a lot more math, and I don't have time to do that. Thank you.